So, this digital signal representation, so this gives us the flexibility by which we can think about digital processing of these signals from the environment. So, these analog signals that we are getting, so if we want to process them digitally, so we have to think about their representation, because anything that you want to do, first of all what is required is to store the information that we have got from the outside world, and for storing the information, so we have to go for this digital form only. So, by using these binary numbers we can represent any quantity. So, we will see in our course that these by the different number systems are possible, and in a computer system the number system that is used is the binary number system. So, where these individual digits are only ones and zeros. So, what we can do this we can represent two different state of some signal by means of these two different notations 0 and 1. So, maybe if it is some voltage value, so we can say that okay, this 0 is 0 volt and 1 is 1 volt, like that, or if it is say 0 is 0 volt, 1 is 5 volt, or it may be 0 is minus 12 volt and 1 is plus 12 volt, or the other way. So, 0 is minus 12 volt, sorry, 0 is plus 12 volt and 1 is minus 12 volt. So, like that we can have different type of conventions that we follow, but ultimately the information that we store, so that is in some digital format. So, for example, you can have this binary 2. So, 2 is represented by 2 bits 1 0, that could represent a 2 volt signal. So, if we say that binary 1 corresponds to a 1 volt signal, so you can say that the binary value 2, it corresponds to a 2 volt signal. So, we generally have to agree on some sort of code. So, that is what I was talking about some time back. So, you can say that say minus 12 volt is 0 and plus 12 volt is 1, or somebody may say that the plus 12 volt is 0 and minus 12 volt is 1. So, both of them are possible. So, if you look into different systems, you will see that all these types or different types of representations are possible. So, we must agree on some sort of coding that we have, and the dynamic range of the signal that we want to represent. So, see, whenever we are talking about some representation of a number, so we are dedicating certain number of bits in it, or a certain number of digits for that purpose. So, using that many digits, so you cannot represent any arbitrarily high number. So, if I say that I have a number system, I have a space to write only say 3 digits. So, I cannot use it for representing the number 2556 in that system, because that requires 4 digits, 4 digit space, but we have only a single digits 3 digit space. So, I cannot have 4 digits there. So, this way we can think about this range. So, this dynamically what the values that signal can pick up. So, we must know that, and accordingly we have to decide the minimum number of bits that we will be using for storing that information. Possible digital representation of a pure sine wave of known frequency. For that purpose, we must choose the maximum value. So, what is the maximum peak that we have, and resolution or error, that is at what level, at what difference of values you are going to take. Okay. So, we will say suppose we want 1 volt accuracy. Okay. So, suppose that is the maximum amplitude is minus is 50 volt, maximum amplitude is 50 volts. So, that is the signal goes from say minus 25 volt to plus 25 volt in the two ranges. So, if we say that the minus 25 volt I will represent as 0, then minus 24 volt I will represent it as 1, minus 23 volt I will represent it as 2. So, like that. So, if we think about this type of levels, then ultimately for this minus 25 volt to plus 25 volt, this 50 volt range, I will have 50 different levels of the signal that we can get. So, if we think about 1 volt accuracy. So, as a result, so these 50 different values have to be represented, and in a binary number system we will see that it will require 6 bits to store that information. So, if you are given less number of bits, so you will not be able to represent these 50 different levels. So, or so you have to suffer on the accuracy side. Okay. So, suppose instead of say 50 different levels, so I want to store I want to have I am given only say 5 bits. So, with 5 bits, so I can have 32 different levels possible only. So, accordingly my accuracy will be less for the signal. So, this way this digital signal representation itself, it introduces some amount of error. So, if we are looking for these exact values, if we are looking for exact values, then we have to go for the analog signals definitely, but as soon as we go for this digitization process, some amount of error is introduced into the system. So, that is there, but we will see that there are different types of errors that can crop up into these analog systems, and that makes the digital systems much better from that point. But as far as the initial quantization is concerned, so digital signals they have got some amount of error associated with it. So, how can we represent digital logical functions in digital representation? So, digital signals they offer an effective way to execute logic. The formalism of performing logic with binary variable is called switching algebra or Boolean algebra. So, when we talk about algebra, so the term algebra means that there will be some values that you can that individual variables can pick up. So, that is there, and I can do some operations on that on those values. So, there will be some axioms or fixed accepted norms for that particular system, and then on that we can build up the total set of computations. So, in case of digital signals, so we will see that this Boolean algebra or switching algebra, so that makes the basic foundation stone for developing the system. And you may be knowing that this Boolean algebra, so this was discovered long below these digital circuits came into existence, and at that time it was pure mathematical interest, but once this digital systems got introduced, then this again this Boolean algebra got its importance back. So, this digital electronics, when we are talking about, it combines two important properties. One is the ability to represent functions by coding the information in digital form. So, that is one property, and the other property is that it can control a system by a process of manipulation and evaluation of digital variables using switching algebra. So, you can do some computation, you can find out you can have a set of conditions for which certain signals are to be turned on. For example, if in a plant control, so there are maybe different conveyor belts moving, then items are being put onto conveyor belt, and then apart from that there may be some fire safety system. So, if a smoke detector is sending signal, so like that there may be a large number of signals, the inputs that you can get from the plant, and accordingly you may have to do a set of other operations. So, in this process they can be represented by means of some logical equation or logical functions, and those logical functions or those control functions, they can be implemented by means of this, they can be represented by means of switching algebra, and once you have represented them using switching algebra, so you can implement them using digital circuits. So, digital signals, so this is the next we go into why digital signals are preferable. So, digital signals can be transmitted, received, amplified and retransmitted with no degradation. So, why do I say so? Because if you are transmitting some digital value, so you know that the ultimately what is transmitted is a bit 1 or 0. So, when you are transmitting a bit as 1 or 0 at the receiving station, so if I say that 1 in my system, 1 is represented by plus 12 volt and 0 is represented by minus 12 volt. So, at the receiving station, so if you get some intermediary value, say minus 5 volt. So, you can say that minus 5 volt is close to minus 12. So, that can be taken as 0. So, that way we can say that even if I have got some values degraded, but digitally the value is not degraded. So, digitally we can still take it back to 0. So, these binary numbers, so they are natural method for expressing this logic variable, and complex logic functions can be easily expressed as binary functions. So, we will as I was telling that in a plant there may be different inputs coming from different regions, and then we can have the overall plant function specified in terms of these control operations that it is doing, and that may be a set of logic functions, and they are represented as binary function, and from there we can get the function implemented in digital circuits. So, we can achieve arbitrary levels of dynamic range, that is the ratio of the largest possible signal to the smallest one can be distinguished above the background noise. So, what happens is that so whenever you are transmitting a signal, there is always some amount of noise that will get added into the system. So, if you are transmitting some analog signal, so you can say that the analog signal, say suppose I am transmitting a value of say 12 volt, and due to this noise, so this value becomes degraded to say 7 volt. So, there is a noise introduced of minus 5 volt and at some instant, and it becomes 7 volt. So, at the receiving end, I do not know whether the value is really 7 volt or it is 6 volt or it is 12 volt or something intermediary. So, that way we cannot find out the thing. But if we say that in case of digital one, so if I know that plus the 1 will be transmitted as 12 volt and 0 will be transmitted at minus 12 volt. So, we can safely say anything above 0 is possibly 1, and anything below 0 volt, so is possibly a bit 0. So, this is the amount of the noise margin or noise immunity that we have in the digital system. So, it is going to be much more compared to the analog system. So, digital and the last point is that digital information, it can be easily and inexpensively stored. So, we can store these values in so with the advancement of this DRAM technology and all, SRAM technology and all. So, we can store large amount of information digitally in the system, and the quality is also much better than the analog storage. So, what do you mean by this analog signal or digital signal? So, the first diagram that you see here, so this is an analog signal. So, over the time, so this it may be a voltage signal or a current signal. So, it is varying like this. So, this is the analog signal. So, analog signals take on continuous values. So, there is you cannot say that at different, there is nothing like at different times. So, this is normally specified in terms of some function over time, or maybe as a differential equation and all, but ultimately this is a continuous function of time. So, typically a current or voltage may be representing an analog signal. Digital signals, so they appear at some discrete levels. So, usually we use the binary signals that it only 2 levels, like here you see that we can have a low level and a high level. So, this may be for this much of time the signal was low, then for this amount, this range of time the value is 1, then again for this range the value is 0, again it is 1. So, one level is referred to as logic 1 and the other level is referred to as logic 0. So, of course, it is not mandatory that this high level should be 1 and low level should be 0. Somebody may say that my high level is 0 and the low level is 1, that is very much possible. But what is required is that there are 2 distinct levels, one of them is called logic 0, another one is called logic 1. So, we have got different this digital signals. So, they are going to be discrete in terms of level. So, it is not a continuous function like that. So, with that, so if we have got an analog signal, so now I cannot have information stored for every time instant in my digital system. Like, so analog signals are continuous in time and voltage or current. So, like say so we can or charge. So, that way we can have these analog signals represented over time. But when you do a digitization, so at every point we basically do a sampling. So, at some regular intervals of time, so we sample this digital signal, and then what we get is over the time intervals, after separated by time intervals, we get some signal samples. So, after digitization, this continuous analog signal, it becomes a set of discrete values only. So, they are typically separated by this fixed time intervals. So, which is known as the which is this typically this is known as the sampling interval. So, after this sampling intervals the value is sampled again and these values are stored. So, ultimately for digital signal, so what we will need to do is that we need to store the values of the signals at these discrete points only. So, if you are willing to do a good approximation of the analog signal, then you have to do a sampling at a much higher rate, and if you are not so, then you can do a sampling at a lower rate also. And from the communication theory you can find out like what is the minimum rate at which we have to do the sampling and all for periodic signals etcetera for reconstruction purpose. The important modules that we have in this process, one is the digital to analog converter, so or DAC. So, digital to analog converter will come when this after doing this digital processing. So, we are trying to give some signal to the environment. So, the environment is analog. So, we have to give some analog signal. So, this n bit digital value that is coming as input to this digital to analog converter module. So, it produces a voltage level. So, you can say that if this in general, so it is if Vfs is the voltage, the full scale voltage from is a Vfs, from 0 to Vfs are the values. Then based on these values that we have got, so if all these B1, B2, Bn, so if all these bits are zeros, then what you get is 0 at the output. So, if you are giving all 0 here, so you are getting a 0 output here. On the other hand, if you are giving all these bits as 1, okay, so you will be getting a very close, you will be getting the expression VO will be very close to VFS. Okay, it is just slightly less than this VFS. So, which is basically because of, so that way you will get a value which is very close to VFS. So, you can say that okay, this is the voltage level that we are getting. So, that you are getting the full scale range. So, that way this digital to analog converters, so they are useful for converting the digital value that we have got after processing into some analog signal for to be sent to the environment. So, what is the smallest possible voltage change? So, since this is a so to change the value you can vary these bits, and since this quantity B n into 2 power minus n. So, this has got the minimum contribution. So, if you are going to change from the smallest possible change that you can do is by changing this flipping this particular bit B n, and that way this minimum change that is possible is the 2 power minus n into VFS. So, this we call the least significant bit or LSB. So, that is this nth bit is the least significant bit or the LSB. So, by changing this LSB we can get this much of change. So, this is the quantum, this is the quantization level. So, you cannot represent voltage change which is finer than this 2 power minus n into VFS. So, you cannot get better than that. So, that way this will have the error part. Similarly, we have so this is another this is a commercial some commercial DAC. So, this is TI is 20 bit sigma delta DAC, then this is an 8 channel DAC from Cyrus. So, like that. So, essentially what is happening is, so this light colored signal. So, this is the analog signal that we have. So, and these are the samples. So, now if you are doing a digitization, so this is basically getting approximated like this, okay. And then so these digital values that we have, so that is converted into levels like this. So, this signal that we are getting is a close approximation of what we actually want, okay. So, that way we say that these digital to analog converters are doing the conversion. The other component, the opposite of this is the analog to digital conversion. So, where on this analog side some value is coming, and then we want to convert it into some digital value. So, like say one conveyor belt is moving and you are just trying to see what is the speed at which it is moving. So, the speed is coming as an analog quantity, some analog for some transducer will be there and it will be coming as a analog signal, and that analog signal we want to convert to digital values. So, that we can do some processing, we can either increase it or decrease it like that. So, that way we can have the analog to digital converter on that side. So, this analog input voltage V x, so it will be converted to the nearest n bit number. So, again the same thing that for a 4 bit converter, so 0 represent the V x. So, if you the 0 to V x, so that will input yield 0 0 0 0 to 1 1 1 1 digital output. So, when you give 0 as input, so you get 0 0 0 0. When you give the maximum value V x as input, so you get 1 1 1 1 as the digital output. So, that is the design principle of this analog to digital converter. So, we will see later in our course how to design these ADCs and DACs in different ways. But however, ultimately this is the thing that we want. So, if we give a 0 voltage, so it should give 0 0 0 0. If we give V x the maximum possible voltage, then it should give all 1. So, output is again approximated approximation of the input data to the due to the limited resolution of this n bit output. So, error that we have, so this is actually the V x that we want to represent, but what we actually get is this one. So, these bits that are coming. So, if all these bits are 1, then you will be getting a value which is very close to V f s, but this value is V f s. So, this V f s minus that approximation, that gives the amount of error that you have in the process. So, this way we can have the analog to digital conversion. So, this DAC and ADC, they are two very important modules that you have in a digital system when it is interfaced with the analog domain. So, we will see that in due course of time. So, if you look into this analog and digital signal, so it seems that we live in an analog world. So, things like we make the statements like louder, quieter, hotter, colder, longer, shorter. So, this is a sliding scale. So, maybe if I say that make it louder, so you just increase, you turn the knob a bit, and maybe I am satisfied, so I say okay, or I say okay, no, reduce it a bit, so make it quieter. So, like that. So, that is an analog signal. When we are recording some sound on a tape recorder, so we are putting the analog signal onto the tape. The digital signals are not on a sliding scale. So, they are either on or off, like the light switches. So, either the switch is on or the switch is off. There is nothing like light is turned half on. Of course, if there may be intensity control of the light, so that may be there may be some some analog some sliding scale may be there. So, if we just look into some of the signals and try to see whether it is analog or digital. So, this volume control on a radio, so this is an analog signal. Traffic lights, so they are either on or off, so they are digital. So, this green, red and yellow, so either they are on or they are off. Motorbike throttle, the amount of fuel injected into the system, so that is going to be an analog signal, because with the press of the as we turn this accelerator, so it puts in more and more fuel. The dimmer switch, so if you can control the amount of illumination, so that is also an analog signal, whereas a light switch which just turns on or off the light, so that is going to be a digital signal. Water tap, so this is again an analog signal. Okay. So, you can turn the tap as much as you want, and accordingly the amount of water passing will vary. Music on a CD is a digital signal. So, CD, the compact disc, they store information on a digital format, and music on a tape, so that is going to be an analog signal, because there it uses analog principle to store the information. So, this way different signals, so you can think about them in digital or analog, but most of the signals or the most common signals that we have, so they are all analog in nature. So, we have to pass them through an analog to digital converter to get the corresponding digital versions, and if we are trying to produce an analog signal through some digital processing, we have to have a digital to analog converter for converting the digital value to analog. So, this is another typical example of analog and digital signal. So, a security floodlight, so it switches on when you approach. So, it may be it has got an analog input. So, it senses the infrared, the amount of infrared that it sees from you, and produces a digital output. So, floodlight is either turned on or off. So, when it is doing that sensing of this infrared component, so that is an analog signal, it is an analog input. but when it is producing this floodlight, once it is turned, or it is either turned on or turned off. So, that is going to be a digital signal. So, we can call it an analog to digital converter in that sense. Okay. So, that is one way of the ADC that you can see. What is the problem with analog signal? It is the noise. Okay. So, the lot of noise gets introduced, like if you are for the sound, there may be a hiss out that get introduced, or if it is an image or picture, this speculate dots may get introduced into the picture due to these errors that or the that got introduced from the noise. So, when we are sending a signal over a long distance, the signal will get weaker, okay, because of losses, and we need to boost the signal. Otherwise, you have transmitted, as I was telling. So, you transmitted a 12 volt, and over the length, so it got reduced maybe so much that you get a very low voltage there. So, that way you need to amplify in between. Okay. So, normally what we do is that we put some periodic amplifiers on the path, and then the amplifier amplifies the signals, it boosts up the signal. So, that at receiving end you get a reasonably correct signal. So, the problem is that we end up boosting the noise as well. So, in the process, so in the if we have got a boosting station, so if previous to that in the previous segment some noise got introduced. So, that noise is will also get boosted up in the process. So, this noise also gets amplified, or noise also get boosted up. So, that is the problem with the analog signal. So, if we on the other hand, the digital signal, so if we convert the signal to digital form and then send it, still gets weaker, and noise will still creeps in, because that is the ultimately what we transmit is some analog voltage values. So, that will be that will make the signal weaker, and the noise will come. So, there is no doubt about it, but it is like this. If you read the text yourself, the software in your brain can reconstruct the text, because you know that so because even the letter shapes are supposed to be even though they are blurred. So, like if you do a photocopy of a page with a page which is not very clear. Okay. So, if you do a photocopy, so after photocopy you will get a even worse page. But if you do it like this, if you read the text from the page, so possibly you will be able to figure out those blurrings of the different letters that you have on the page, and we can just correct it. So, this is just what this digital thing does. So, maybe the voltage value has reduced a bit, but it is not that much degraded, and still possibly we can figure out that this was a 1 and this was a 0. We can reconstruct the signal and then again transmit. So, that way the amount of noise that got introduced, so that may get reduced further. So, analog signals, they suffer from noise, but do not need such complex equipment. On the other hand, the digital signals need fast, clever electronics, but we can get rid of any such noise. So, this is the that tells the summarizes the analog and digital signals. So, one of the very basic components when we are doing this digital switching and digital circuits, so is a transistor, and the most recent transistor that is being used in the digital industry today. So, they are CMOS transistors. So, in CMOS transistors, so we will discuss in detail later. Just to tell you how it works. So, this is a semiconductor block. Okay. So, that is normally, so this is on that semiconductor block we have got two dedicated region, one is called a source, another is called drain. So, they have got some type of impurity diffuse, they are some types of diffusions basically. So, if this semiconductor block that we have, so if this is of say p type semiconductor, then on these two regions, so we put some n type diffusions. So, one region is called source, other region is called drain. So, the region in between, so it is covered by some silicon dioxide layer, and on top of that we put another layer of polysilicon gate. Okay. Now, normally what happens is that if you apply a voltage onto this gate, okay, positive voltage onto this gate, so it will attract the electrons from this substrate, we call it a substrate. So, it will attract these electrons into this channel between the source and drain. And now, if there is a potential difference between source and drain, so if you apply a battery between the source and drain, then these electrons will move through this channel, they will go from source to drain or drain to source depending on the polarity of those signals. So, you get a current flow through the device. So, if you apply a positive voltage here, so it will attract electrons, turning the channel between source and drain into a conductor. So, this region will behave as a conductor. So, that is why it is called a semiconductor. So, will be so if you turn for turning off the conduction. So, you just make the gate 0, and so this this channel will go. So, there is no conduction, and if you want this channel to be on, so you just apply a voltage here. So, this channel becomes on. So, pictorially it is represented like this. So, we have got source and drain at the two ends, and there is a gate control. So, if you apply logic high here, high voltage here, then the channel will come into existence. As a result, you can see that as if this transistor is now open. So, the transistor is now on. So, you can get a conduction from this side of the transistor to this side of the transistor through the channel. On the other hand, if you put a logic 0 here or a low voltage here, or you withdraw the voltage that you had applied. So, this channel will not exist. As a result, this transistor will behave as if the transistor is open. So, this will behave like a open switch. So, in one case it is working as a closed switch when this gate is high. So, this will act as a closed switch. So, you will get connection from here to here, and another case you will getting an open situation where there is no connection from gate to drain to source. So, this way this transistor will behave in the form of a switch. So, we will come back to these transistors again later, but what I essentially mean is that these are these small transistors. So, they are the tool by which we represent these switches in the digital circuit. So, they will be used again and again for whenever in the circuit design.